You're watching a Channel 98 NBISD TV production.
Hello friends out there in TV land, welcome to another fascinating, exciting, mathematically invigorating episode of That Geometry Show. I'm your host Kevin Corpy, and today we're going to be talking about, guess what? Take a wild guess. Triangles all over again. It's been like 100 weeks that we've been talking about triangles, and you're probably getting sick of them. But you know what? I don't care. If you're getting the lessons every time, that means you're probably getting good at them too, and that's the important thing. Today we're going to be talking about a triangle inequality theorem, and I really hope I do it justice. So download those documents from the district website, www.newbraunfels.txed.net, and we'll get going. Lesson 13, lucky number 13. It's going to correspond with your Glencoe Geometry chapters 5.4 and 5.5, all about the triangle inequality. By the end of this lesson, you should be able to, number one, recognize and apply relationships between sides and angles in a triangle, and number two, apply the triangle inequality theorem. Big theorem. Big voice. All right. Now, we learned previously on another episode that if sides in a triangle were congruent, then the angles that are opposite those sides are also congruent and vice versa. So we've been working with congruent triangles, which means equal measures up to now. Well, there are also important relationships that deal with unequal or non-congruent quantities. And today we're going to examine two of those important relationships. The first relationship involves the lengths of the sides of a triangle in relation to the triangle's angles. Okay? So, here is the all-important theorem. Here's what it says. It says, in a triangle, triangles again today, the longest side is across from the largest angle. The shortest side is across from the shortest, that's probably not the best word. How about the smallest is a better word? The shortest side is across from the smallest angle, and the middle or medium side is across from the middle or medium angle. So there's a correspondence between the relative sizes of an angle and the size of the side opposite it. Okay? Now let me show you how to use that theorem. Let's look at this example here. Suppose that we want to know which side of this triangle is the longest. Well, we have triangle ABC, and it's hard to see, but we know that this angle here is 80 degrees. And we know this angle, angle C, is 40 degrees. Okay? We don't have any of the side lengths, but by our little theorem here, we can figure out which side is actually the longest. Well, first we're going to have to know what the measure of angle B is. Okay? So we know that the sum of the angles in any triangle must add to 180. So 80 plus 40 is 120. So to get to 180, we have to have this angle here, the missing angle, equaling 60 degrees. Okay? So now we have all three angles, and notice they're all different. Inequality. Well, if we're trying to find the longest side, really all we have to do is look for the biggest angle, because the longest side will be across from the largest angle, and that's going to be 80 degrees. So across from 80 is the side CB. So the answer is segment CB is the longest side in the triangle because it's opposite the largest angle. What would the smallest side in the triangle be? I hope you said segment AB because it is opposite the smallest angle, 40 degrees. Okay? And then the medium size length would be opposite the medium or the middle angle, 60, and that would be segment CA. So you see the relative relationship between an angle and the side opposite. There's a preservation of the order there. 40, 60, 80 is going to be the relative size of the increasing angles, and so we're going to have AB being the smallest. We can write it as an inequality. We can say AB is the smallest, and the next largest would be the side opposite 60, which is AC, and the largest side would be CB. And we can actually write this as an inequality. These are line segments, so let's not forget to put the bar over it. And if I use less than symbols here, this is going to be increasing order. Okay? So AB is the smallest. It's less than AC, which is less than CB. If we wanted to do it in decreasing order, we would have to start with the largest side, which would be CB. AC is still the middle, and AB with our segments over the top. And now we'd have to flip the inequalities. CB would be the largest side, which is greater than AC, which is less than AB. So using inequalities is a nice way to list things in increasing order. The second important relationship involves the lengths of the sides of the triangle. And this is the big theorem here. It's called the triangle inequality. And here's what it says. It says the sum of the lengths of any two sides of a triangle, any of them, must be greater. That's strictly greater. Not kind of greater, not equal to, but strictly greater than the other or the third side. Okay? That's real important. Let's put that into use. Suppose we want to know the lengths of the two sides of a triangle. We want to first find the possible lengths of the third side. Okay? So this side is 5, this side is 9. We don't know what this is. And we want to figure out what possible values x could be. Well, our theorem says that if I add any two sides together, their sum must be strictly larger or greater than the third side. So I can kind of just start by picking the two numeric sides, 5 plus 9, which turns out to be 14. That has to be greater than x. So 14 has to be greater than x. We can flip that around and say that x then has to be less than 14. Okay, that gives us an upper bound. Now the question is, we know we can't go larger than 14, but how much smaller than 14 can we go? Let's look at a combination of some other sides. Let's look at this one here, 5 plus x. The sum of those two sides has to be strictly greater than 9. Now I have a little inequality that I can solve. If I subtract 5 from both sides, I get x is greater than 9 minus 5, which is 4. This gives us now a lower bound. That says x has to be strictly bigger than 4. Well, let's look at the other combination before we make a concluding statement here. 9 plus x has to strictly be greater than 5, and subtracting 9 from both sides, I get x has to be greater than 5 minus 9, which is negative 4. Well, that's a no-duh statement because negative sides don't make any sense in a triangle because we're talking about length. So that one doesn't really give us any information. So here we go. Our upper bound is 14, our lower bound is 4. The nicest way to give the range or the interval for the possible values of x is to write it as a compound inequality. This is basically saying x has to be between 4 and 14. So you can physically write x between 4 and 14 in increasing order. And then if you just put your little less than inequalities there, you have it. This basically now says that x has to be greater than 4 and at the same time less than 14. So any value between 4 and 14 will work in this triangle. The sides will meet up and we'll actually have a triangle. For instance, 7, 8, 11, any of those will work. Okay? Now, while there are other inequality relationships other than the two that I just talked about, the two that we just talked about are the most important. They're the most commonly used. So you need to be sure that you learn those two relationships and then you'll have nothing to worry about. You'll be set. Okay? Let's do some rapid fire here. Let's get going pretty quick. Number one, which of the following could represent the lengths of a side of a triangle? Well, this is going to be the triangle inequality. We just need to check all the combinations of two sides added together and make sure it's larger than the third side. So let's take choice A. If I take the first two numbers, 1 plus 2, I know that's 3. And the inequality says if it's a triangle, that has to be strictly larger than the third side, which is 3. So let me ask you at home, is 3 bigger than 3? No, it's not bigger than 3. 3 is equal to 3. And so the inequality says, or the theorem says, it has to be strictly larger than. So that's not going to work. As soon as you find one combination that does not meet the standard, then it has no chance of being a triangle. So even though in this case, if I would have chosen 2 plus 3, the other two side lengths, that equals 5, and that is greater than 1, we have to check all three, and they all three have to pass. So we found one that failed, moving right along, not the answer. Coming over here to 6, 8, 15. Let's try adding 6 plus 8, the two smaller sides, or the smallest sides. That's going to give us 14. Is that, question mark, greater than 15? 14 bigger than 15? No, no, that's not going to happen. Not going to work. We found one side length that failed. That's not going to be the triangle. So if one of these is true, it has to be choice C. Are we going to go on to the next question yet? No, we're going to verify. We have the time. 5 plus 7. What does that equal to? That's equal to 12. Is 12 greater than the third side 9? Yes. One of them is passed. Now let's take the combination of 5 and 9. 5 plus 9, that's 14. Is that greater than the other side 7? Absolutely. And then finally we'll look at the 7 and 9 combination. 7 plus 9 is 16. And is that greater than 5? You betcha. So all three of them passed. 579 then appears to be a legitimate triangle. Number 2, two sides of an isosceles triangle measure 3 and 7. Which of the following could be the measure of the third side? Ooh, isosceles triangle. Let's draw one. The simplest one to draw is like this, where these are the two congruent legs. And hypothetically, I know one is 3 and one is 7. Let me just call this one 3. Now, can I call this side 7 right here? Absolutely not, because these are the congruent sides. So if I'm calling this one 3, this one has to be 3, which means the other one has to be 7. Now, just because you could draw it and label it, and notice it's not drawn to scale, you can't say that it's a triangle. You have to check. Because it's not drawn to scale, we have to check to see if it passes all three conditions. So let's take the two smaller sides. It's really, really convenient to start with the two smaller sides. So 3 plus 3, I know that's 6. Is that greater than my third side 7? 6 bigger than 7, that is laughable. Ain't going to happen, okay? So the actual triangle must have still been isosceles, but 3 must have not been the leg. That must have been the side that was 7, making this one 7, on the other side 3. Notice it didn't say which one was 3 and which one's 7. Now this could be a triangle. Let me check. The two smaller sides are 3 and 7. 3 plus 7 is 10. Is that greater than the other side 7? Yep. I can check the 7 and 7 combination. That's going to be 14, which is greater than 3 for sure. And the other combination is 7 plus 7, deja vu. It's the exact same one because two of the sides are the same. So 14 is still greater than 3. That's the great thing about math. It doesn't really change from problem to problem. Rapid fire. I'm trying to keep it rapid. Number 3. In triangle ABC, the measure of angle A is 30 and the measure of angle B is 50. Which is the longest side of the triangle? Well, we do have to have a triangle so that we can label something. So I'll just call this A, this B, and this C. Now I know measure of angle A is 30, the measure of angle B is 50. What's the longest side of the triangle? Well, I know right away that side AC is going to be bigger than side BC because 50 is larger than 30. But what about angle C? I don't know what it is. So we know that the sum of the interior angles has to be 180. So 50 plus 30 is 80. And so that leaves this angle C to be 100. Now again, notice my picture is not drawn to scale. The only thing that we need a diagram for is so that we can kind of get our referencing down. But the numbers are going to tell the truth about the triangle. 100 is the largest angle, so opposite that angle is the largest side. So the largest side is segment AB, and the answer choice must be A. Moving along, in triangle DEF. Where's triangle DEF? It's not here. We have to draw it. Okay? Triangle DEF, I'm going to call that D, E, and F. We have an exterior angle at D. Well, to get the exterior angle, we have to extend this side out here, and this is our exterior angle. And it says that that is 170. And it says also the measure of angle E is 80 degrees. So I'm going to label that. And now what's the longest side of triangle DEF? Well, remember that this angle here and this angle here form a linear pair. They're supplementary, so they have to add to 180. So if this is 170, this has no choice but to be 10. Now that I know this is 10, the sum of the interior angles has to equal 180 also. So 80 plus 10 is 90, which means that this angle here has to be 90 degrees. It's a right angle, again, even though it doesn't appear to be. So now I have 10, 80, and 90. So the longest side will be the side that is opposite the biggest angle, which is opposite 90. So that is segment DE right here. DE is our segment, and it's answer choice C. Number 5. In triangle ABC, the measure of angle C is 55, and look at this. Angle C's measure is bigger than measure of angle B. What's the longest side? Ooh, okay. This one looks fun. Kind of vague and interesting all at the same time. ABC, I draw my triangle, just something to label. Angle C now is going to be 55. Okay. Now we know that the angle of C is bigger than the measure of angle B. We're trying to then determine what a possible measure for A would be. Well, here's what we could do. We could do worst case scenario. Let's assume that angle B, or the measure of angle B, is as big as possible. Okay? Let's say it's actually 55, which would make it the same as angle C. So if that's 55, those two add to 110. So the measure of angle C plus the measure of angle B equal 110. Which means when B is at its maximum, A would be at its minimum. So that would be 110. To get to 180 means I'd have to go to 70. So that would be a possible angle for angle A. But this is the smallest that it could be. Okay? Angle A is at its smallest when angle B is at its largest. So which is the longest side? Well, that's all we need to know. Because this is going to be 55, this one's going to be less than 55, and this angle here has got to make up the difference for whatever B is not equal to, so it's going to be 70 or bigger. In any case, it's the biggest angle. So the side opposite, BC, this one here, is the longest segment, and our answer is C. Woo! Time to cool off from that rapid fire round. That was a lot of practice right there in a row. So let's take a break. Don't go anywhere. Watch the public service announcements and come back right here. We'll be waiting.
Yesterday, my friends told me to smoke some weed, and I did. Then today, they said I should try to outrun Tick-Tick, the little lumberyard dog. And I don't think I can. I'm an idiot. I'm doing stupid stuff, and that ain't me.
No! Live above the influence. Above them, above weed.
Okay, I hope you're well rested in that short break there, because now it's time to do some challenging type problems. Time's a-wasting. Let's do it. All right. Number one on the challenging problem section of the show. In triangle GHI, we have angle G is equal to this, measure of angle H is this, and measure of angle I is this. They're basically three algebraic expressions. Which inequality shows the relationship between the lengths of the sides of the triangle? Well, I need again something that I can label. So a generic triangle here, GHI. And I'm going to go ahead and label the algebraic expressions. Angle G is 6x minus 3. Angle H right here, I'm writing it on the outside, so there's room, 10x plus 8. And the measure of angle I is 49 minus 2x. Now, remember what we know about the sum of all the interior angles. They must add to 180. We have each of the angles in terms of a common variable, x. So with a little bit of algebra, I can create an algebraic equation. So starting with no particular angle, I know that 6x minus 3 plus the other angle, 10x plus 8, plus the last angle, 49 minus 2x, has to total 180. So now I'll collect my like terms. I like to underline the like terms when there's a lot of information there. So 6x plus 10x is 16. 16 minus 2 is 14x. And then maybe a double underline for the numbers. I've got a 3 plus 8 plus 49, which is going to be 54. And that equals 180. Now I can subtract 54 from both sides, and I get 14x equals 180 minus 54, which is 126. And dividing both sides by 14, I get 126 divided by 14, which makes x equal to 9. So 9, I feel like I have accomplished something because I've solved for x. That's what we did all through algebra. But we haven't really answered the question. Now I can actually get what the relative measurements of the angles are. And I'm going to redraw the triangle just so it's not so cluttered. All right? So now I can plug 9 back into each of the expressions. Angle G is 6x minus 3, or 6 times 9 minus 3, which is going to give me 51. Angle H is 10 times x, or 10 times 9 plus 8, which is going to give me 98. And angle I is 49 minus 2x, or 49 minus 2 times 9, which gives me 31. And now that I know all three angle sides, we're looking for the relationship. Notice your choices have greater than and less than. I'm going to go ahead and just list mine in increasing order. So I'm going to start with the smallest one. If 31 is the smallest angle, the side opposite it, which is GH, is my smallest side. And then my next largest angle is opposite, or 51. So the side opposite it, HI, would be my next largest. And opposite the largest angle is the largest side, so that would be GI. And I would put less thans in there because it's increasing order. Now I'm going to look to see if my choice is up there. GH would be first on the less than, so it could be this one or that one. Next, I want to be less than HI. Hi, hello out there. This one has GI, so this one's wrong. So let me check the last one, less than GI. Boom, I got it. So it has to be choice C. Let's say it wasn't either one of those two choices. Notice the other two choices above that I haven't looked at are greater than. So I can flip this whole thing around and start with GI, and now that would be greater than the middle, and then greater than the smallest, GH. And so then you could do the same piece-by-piece analysis with the greater than inequality. So they're both equivalent. One's just writing in increasing order on the first and decreasing order on the second. All right, the second and final challenging problem of the day. In triangle PQR, we have vertices at these points, and we're trying to find which angle has the smallest measure. Ooh, angle has the smallest measure. Well, the first thing I want to do is actually plot the points. I have a coordinate plane here, so the point P is at -4, 6, so that's going to be right here. I'm going to label it, and I'm also going to write the ordered pair next to it just because it's going to be easier to reference. Point Q is the point 4, 5, which will be right in here, and label it Q and call it 4, 5. And then finally, R is -2, -3, which puts me down here in quadrant 3. Again, labeling it as R and putting the coordinate next to it. Now, all I have to do is connect the dots here with a straight line, which I'll freehand here. And voila, it's a triangle. Okay? Now, we're trying to find which angle has the smallest measure. So the theorem says that opposite the smallest angle is the smallest side. So opposite the smallest side should be the smallest angle. So we need to find the side lengths here. Well, that's going to require us to use the distance formula because we're on the coordinate plane. The distance, basically, from this point Q to this point R is going to be the length of that side. So recall the distance formula from a previous episode. It's the square root of the change in x's squared plus the change in the y's squared. So now I'll go ahead and find the distance between each of the points, which is going to be their side length. So I'm going to start with segment QR. Its measurement is going to equal the square root, the change in the x's, 4 minus -2, squared, plus the change in the y's, 5 minus -3, squared. So that's going to give me the square root of 6 squared is 36, plus 8 squared is 64. That's going to be the square root of 100, which we know to be 10. So I'm going to go ahead and label this right here as 10. Okay? Is that big? Is that small? I don't know. Just getting a visual here, because we are on a coordinate plane, we can actually kind of interpret. It looks like 10 is going to be bigger than this side, but maybe not this side. Okay? So let me go ahead and do the other calculations. I'm going to do PR next because it looks like it's going to be the serious contender. The square root of 6 minus 5 squared plus -4 minus 4 squared. And I'm going to go right to the actual calculation just to save a little bit of time. But we do it similar to above. It's the square root of 85, which is approximately 9.2195. So it's a little bit smaller. It's about 9.22. We can round to 2 decimals in this case. So now the question is PQ a contender? Let's find the measure of PQ. PQ is going to be the square root of 6 minus 5 squared plus -4 minus 4 squared, which is going to come out to be the square root of 65, which is approximately 8.062. So again, just labeling this side here as 8.062. Now the smallest angle should be opposite the smallest side. Well, 10, 9.2, and 8.062. This is the smallest side. So the angle opposite it, right here, angle R, would be the smallest angle. So the answer choice, way back up here, is angle R. Required the distance formula, 3 different calculations. All right, now it's time for the part of the show we call the Say What? And it kind of relates back to what I did on a previous episode, actually the first episode when I talked about the Egyptian rope stretchers. Remember what they did is they actually had a rope that was tied off in equal knot segments. And they knew that by stretching the rope at different knot points, they can create not only triangles, but right triangles because they knew the Pythagorean triples. Okay? Well, we're going to look at a different problem today, and we're just trying to make generic triangles, not necessarily right triangles. So here's the scenario. We basically have a rope that has 10 knots in it, one at the end, one at the other end, and some in the middle here, and that's going to partition it or divide it into 9 equal segments. We're interested in knowing how many different triangles we can make with this rope. Okay, so we have to have a plan of action. If you actually had a rope, you could do trial and error, and you can bend the rope at different points and try and make it connect up. Well, here's our plan. We're going to let X, Y, and Z be the length of each of the sides, 3 sides of our triangle. Then we're going to check every possible combination so that the sum of the 3 sides is 9. If our sum exceeds 9, we are not using the same rope. Okay, there's 9 equal segments. Now to see how many triangles we have, we're going to use a table to help us keep track of the combinations. And setting up the table itself is a skill. I have it set up just to save a little bit of time, but basically we're going to systematically let x, our smallest side, be the smallest number, and we're going to let y be the smallest possible number. So that gives us a side length of 1 and 1, and then because they have to add up to 9, the other side would have to be 7. Okay? I'm going to go ahead and talk about the combinations quickly, and then we'll come back and do the test. So now leaving x to be the smallest side and increasing y by 1 to get 2, we have 1 and 2, which makes 3. So it has to add up to 9, so z was already predetermined now to be 6. So continuing the pattern, I have a 1 and 3, which gives me 4, so to make 9 I get 5. 1 and 4 give me 5, so to make 9 I get 4. Now I'm not going to do the 1-5 combination because 5 and 1 are already up here, and 1 and 6 are already up here, and 1 and 7 are already up there. So we don't want to repeat those scenarios. So then I would jump to the next size increment on x, which would be 2. I don't want to start with 2, 1 because I already have the 2, 1 scenario right here. So again, continuing that pattern and making sure it adds up to 9, we get all the way down to 3, 3, 3. Okay, now the important part is to check to see if these actually form triangles by using the triangle inequality. Remember, the sum of any 2 of the sides has to be strictly larger than the third. As soon as we find one that doesn't work, then we know it's not going to be a triangle. And remember, it's a good strategy to start with the 2 smaller sides, or the 2 smallest sides. So let's go ahead and do that. 1 plus 1 is 2. Is 2 greater than 7? Not even. So this would be a big time no, it's not a triangle. 1 plus 2 on the next one is 3. Is 3 greater than 6? No, that's also a negatory. Next one, 1 plus 3 is 4. Is 4 bigger than 5? It's getting closer, but still not going to happen. Down here, 1 plus 4 is 5. Is 5 bigger than 4? Yes. So let's try the other 2 combinations. The 1-4 combination would be 5, which is still bigger than 4. And the 4-4 combination would be 8, which is bigger than 1. So it looks like, yes, we have
2 is 4.
Is that bigger than 5? Absolutely not. As soon as we find one that doesn't work, we can make a concluding statement. Next one, 2, 3, 4. 2 plus 3 is 5. Is 5 bigger than 4? Yes. Checking the other combination. The 2-4 combination gives me 6, which is greater than 3. And then the 3-4 combination is 7, which is greater than 2. So look at there. We have another triangle. And finally, we have the 3, 3, 3. But I repeat myself. The equilateral possibility. Let's check it out. 3 plus 3 is 6, which is greater than 3. And then taking this 3, 3 combination, 3 plus 3, still great, or 6, which is still greater than 3. And finally taking the last 2 3s, adding them together, I still get 6, which is still greater than 3. So yes, and I'll put a double exclamation point because not only is he the final triangle, giving us 1, 2, 3 possibilities, but that's the last problem of the show. So that might be cause for excitement. I hope you had fun. I hope you learned something, and I definitely hope that you'll join me again next week for a fascinating, exciting, mathematically invigorating episode of That Geometry Show. Until then, I'm your host, Kevin Corpy, and I'll catch you on the flip side.
You're watching a Channel 98 NBISD